Hello everyone, and this is my first ever AP Physics tutorial video that I have made. And this is going to be covering separable differential equations, specifically under a drag scenario. So, when I first started AP Physics C, as someone who did not have any calculus experience, I did not know how to integrate or do separable differential equations. As a result, I was completely lost, and I had no idea how to do these until like the end of the semester. So I hope to walk you through this scenario and help enlighten you on separable differential equations. So in this case, we are asked to find a expression for velocity in terms of time, as this person is falling from like an airplane or something like that. They are experiencing two forces, a force of gravity, which is equal to mg, and a force of drag, which is opposing gravity, which is equal to kv, where k is just some drag constant, showing that velocity is proportional to the force of drag. So, this graph right here, some of you may have seen this before, but this is a graph which shows the terminal velocity of this person. So I'm just going to give it to you all right away. The terminal velocity is equal to mg over k, where this graph approaches this terminal velocity asymptotically. Additionally, we can have a velocity that starts above the graph and comes down like this, and our derivation will work just the same. But just for simplicity's sake, I will have this velocity down here, which is going to be less in magnitude than the terminal velocity. So how do we go about starting this? It seems kind of daunting, and it's actually a very simple start. It's just F equals ma. And you may be surprised, why do we have acceleration here when we're trying to find velocity? This is actually where the integration comes in, because the derivative of velocity is acceleration. So we have dv dt, which is the time derivative of velocity, is acceleration. This is where our v variable comes in. So rewriting this, I have F equals m dv dt. Now, what I want to do is I want to expand out this net force right here. So we have our net force, which is equal to Fg minus Fd, because they are in opposing directions. So Fg minus Fd equals m dv dt. Now I want to expand out these forces so that I am working with the proper variables. So mg minus kb. So now that we have this, and we can see that we have our variable for velocity right here, and our expression for the derivative of velocity, we can actually begin our separation of variables. Before I do that, I'm going to simplify this expression a little bit by dividing by m, so that if I divide on m on both sides, those two m's on either side cancel out, and then we're just left with this expression, which is a little bit more simpler. So when I am setting up this equation, I'm actually going to try and get this velocity variable by itself, where it's just going to be velocity times some like constant right here. The reason why I want to do this is I want to avoid something very tricky, which is called U sub. U sub is essentially a method for reversing the chain rule. What is the chain rule? Well, the chain rule is something that happens when you take the derivative of a function where it has another function which resides inside it. So we're going to, let's just say we take the derivative with respect to x of this composite function. What we have right here is we have f prime of x of g of x times g prime of x. So this is essentially the chain rule where this chains out of this function and it gets multiplied by a derivative. Well, what u sub does is essentially reverses this process. But I don't want to do that because that is a lot of work. So what I'm going to do is I'm going to manipulate this so that I don't have to do u sub. So going back to here, how can we do that? Well, as I said earlier, you can isolate v to be by itself. The reason why doing this gets rid of u sub is because it just gets rid of chain rule entirely. So let's say if we get v by itself and then we just have some jumble of constants over here. We want to take the derivative of this, so d dv, so we're taking it with respect to v. Well, this derivative of this is just, the derivative of this is just going to be 1, and then the derivative of any constant is just 0. So this 1, when we multiply anything by 1 in our expression, is essentially going to go away. So we don't actually have to care about this chain rule or u sub that is happening when we isolate v. In order to isolate v, we just have to do some algebra right here. So right here, I'm going to factor out negative k over m from this side. So we have this. So in order to factor out from g, we have to take like the reciprocal of this. So I'm going to write it like this. Notice how, like, if we distribute that back in, it's going to cancel out all of this. So like negative boom right there. So that's all good. So now we have our v right there. And then dv dt. Now we are almost ready to integrate. All we have to do is take this and put it, this expression right here and put it onto this side, and then take this dt and put it onto this side. The reason why we want to take this expression and put it onto this side is because we have our differential here. We want to integrate this expression with respect to v. So we have to have our differential and our variables, which have the v's inside them, on the same side. And then we have our dt going over to this side, since it's just going to be cleaner to integrate that way, as this is not going to be in the denominator of a fraction anymore, and it's going to be on the completely other side of the equation. Now we have negative k over m, and then dt equals dv over this. All right, so now we have our expression like this. We are actually ready to integrate both sides because we have separated the variables successfully, because we have the velocity term with the dv, and then we actually don't have a time term, but that doesn't matter because like this is just a constant, and whenever we take like the integral of like a differential like this, the variable actually just pops out like this, and then plus some constant of integration if you're doing an indefinite integral like this. So right here, we're not actually going to do an indefinite integral. We're going to do a definite integral with some bounds here, 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 and here. So what are these bounds? Well, let's look at these initial conditions. So our initial time is actually going to be 0 right here, and we are going up to some general time t, which we are plugging into our velocity function. So this side is perfectly fine now. So for this one, we have our initial velocity as v naught, as previously stated on the top right here. So you can see in this diagram. Additionally, we are going to be going to some general velocity, which represents the final velocity of some, which is some function of t. So now we need to find our antiderivative of each of this stuff inside of here. So let's start with this side, because this side's going to be much easier. So as previously stated, all we have to do is just kind of have this t that pops out of there, and then 0 to t. Perfect. So here's our bounds notated by this vertical bar, and then there's our, there they are right there. So right here, this integral is actually pretty simple as well, especially since we got rid of the possibility of u sub by isolating this v over here. So this integral is actually just going to be ln, the absolute value of v, minus mg over k, and then have our bounds right here. So v naught to v. Make sure not to confuse these vertical lines. It might seem pretty obvious to some of you, but when I was first learning, I was really confused by all the vertical lines, because this vertical line right here represents the bounds that are on the antiderivative, and then this vertical line is just the absolute values. That's all that does. If you wanted, you could have parentheses around here, but I think it looks cooler like this. Okay, so now let's plug in our bounds over here. So we have negative kt, which is our top bound, minus, and then minus k over 0, k times 0 over m, which is our bottom. So this actually goes to 0. So all this side is just this expression right here. So now on this side, we have v minus mg over k, which this is from our top bound, then ln of v naught minus mg over k. This is our bottom bound. Okay, so now what we have to do is apply a log rule. So whenever we have two logs, I'm not sure if it's actually ln's or just logs in general, but in this case, if we have two of these subtracting each other, they're actually equal to the ln of this stuff divided by this stuff. So what this would look like is something like this. And this helps simplify our expression greatly. It makes it much easier to continue integrating. Or I guess continuing to find the expression. We already integrated. All right. So now we need to exponentiate both sides, which is just taking the exponential of this stuff and this stuff at the same time. So now on the left side of the equation, we have e to the negative kt over m equals, and then this and this are going to cancel. So we just have this mg over k, and then v naught mg over k. So there's this pesky absolute value bars that are kind of stopping us for ultimately solving for this velocity right here. But that is actually no issue. The reason why is because the stuff on the inside right here is actually always going to be positive. The reason why we know this is because in our situation up here, our final velocity at any point is always going to be less than the terminal velocity. Same with our initial velocity. So when you have a smaller number minus a larger number, this is going to be negative. Same thing with the bottom. Additionally, if we want to consider situations where you're starting faster than terminal velocity and then you reach terminal velocity still asymptotically, this still actually works. The reason why is because the velocity initial is greater than this, and any velocity like here or here is still going to be greater than this. So in that case, we would have a positive and a positive. So in the either case, this stuff on the inside is always going to be positive. So we can actually just straight up get rid of these absolute value bars. And now we can easily simplify this expression. So this expression, I'm going to spare you all the algebra, but it would pretty simply simplify to mg over k plus v naught minus, oh wait, hold on, got this parentheses, mg over k, and then times negative k t over m equals like the velocity right here. So this is our expression that we have successfully derived using separable differential equations. I hope this video helped out a bit, and good luck on your deriving journeys through AP Physics C.